All right, welcome to 12.5. We're going to work backwards from the roots to find a quadratic function today. Now you'll see that normally we would be given a graphing piece of paper today in class. It's not critical at all that you have that. If you have the notes printed out from Schoology, then it's not a problem at all. For the rest of you working on paper, still not going to be a problem. All right, so this is what we did yesterday. You're going to find the roots of the function by factoring completely, although yesterday's were not functions, but you do them the same way. Yesterday's were equations that already equal 0, or you were forced to make them equal to 0. This says factoring completely, so that's a hint. There must be a common factor. In fact, there is a 2. And so the roots of this quadratic function, the values of x that will make the equation equal to 0, are 7 and -2. So what we're going to do today, I'm going to give you the roots, like 3 and -5. Then you are going to use that to create two factors. So for positive 3, right, you write x minus 3, because that's 3 would make x minus 3 equal to 0. For -5, you write x plus 5. So you're really writing the opposite, right? Because that's what -5 would make that equal to 0. Then we're going to FOIL it. X times x is x squared. X times 5 is 5x. Minus 3x is 2x. -3 times 5, -15. So if I give you the roots, you can find a quadratic function. There's more than one quadratic function with those roots. So try this one. So positive 7 would make the factor x minus 7. -5 would make the factor x plus 5. We're going to write a function for this and FOIL. So f of x equals x squared plus 5x minus 7x, -2x, -7 times 5, -35. This only has one root. That means it had two factors that were the same. So the function would be x squared minus 2x minus 2x minus 4x plus 4. So you're going to draw a sketch now of our function that has roots at -3 and +1. So there's a root at -3 and there's a root at +1. So how do we find the rest of this function? Well, we need the actual function. And we're going to use -3. So that goes with x plus 3, right? Because -3 would make that equal 0. 1 goes with x minus 1. We're going to FOIL it, right? It's a function today, f of x. So f of x equals x squared, outer, -1x, inner 3x, plus 2x, minus 3. Ah, there's our y-intercept. So we can plot the y-intercept. So 0, -3. We also know, for those who were absent last Thursday, Adam, I'm talking to you, that there is an axis of symmetry that goes right down the middle of the two roots. Everything in a parabola is symmetrical. So if we have this y-intercept, we also have a point on this side that's a parabola. We also know, because this is positive, that this parabola opens up. So we need one more thing. We need the vertex. Well, the vertex is clearly on x is -1. We found that because the vertex has to be on the axis of symmetry, which is right in the middle of the two roots. And so we can put -1 into our function, f of -1, -1 squared with parentheses around it, plus 2 times -1 minus 3. -1 squared is 1, 2 times -1 is -2, right? So 1 minus 2 is -1, right? Order of operations here. And then -1 minus 3 is -4. So the vertex is located at -1, -4, right? Where we thought it would be, right there. For those who don't have the printout, you're just going to draw a sketch of this, because that's all this is. We're not getting every single point along here. And now we have a sketch of our parabola. Turns out that is only one of the quadratic functions that has those roots. There are many more. When you multiply every term of a quadratic function by the same number, you will get a stretched quadratic function that has the same roots. So we're going to do 2 times f of x here, which means you do 2 times every term. So x squared times 2, 2x squared. 2x times 2, 4x. And 2 times -3, -6. So 2fx has the exact same roots. If we factor that, right, you'd factor out the 2, you would get the exact same roots, right, as 1 and -3. But look at the y-intercept now. The y-intercept is down here at 0, -6. There's the symmetrical point is across from it. Notice the axis of symmetry hasn't moved. The roots haven't moved. But what has moved is everything else. And there is our stretched quadratic function. If you did it, multiplied it by 3, you would get an even more stretched function. So this is the function that's listed there. F of x equals x squared minus 4x plus 4. It has one root at 2. So multiply that. You could do some other thing, but we want to fit it on the graph. So let's do 2f of x, which is 2x squared minus 8x plus 8. So now, look at the y-intercept. It's at 0, 8. The axis of symmetry will be the same, so there'll be a point right there. So notice when you stretch it, it gets skinnier as well. The root will not change. It has the exact same root. And there's our new linear function. You're just drawing a little sketch of that. The green one here is if I multiplied by 3 and did 3f of x. You would get 3x squared. I'm multiplying the original one by 3 minus 12x plus 12. The y-intercept now is going to be up at 0, 12. And notice it gets even skinnier. So now we want to write a function that is upside down. So what would you multiply by to flip the function upside down? Well, it would be any negative number, because if you multiply by a negative number, right, let's do -1, right, you would get negative x squared plus 4x minus 4. Notice there's our new y-intercept. Right, when you have a negative a, the parabola is upside down. So if you multiply by a whole number, it stretches. If you multiply by a fraction, it shrinks. So let's do 1/2 f of x here, or let's do it in red, or let's do it in blue, since it's going to be in blue when I graph it. So it's 1/2 f of x. So half of 2 is 1, half of 6, or -6 is -3, Half of negative 8 is 4. And that is called a vertical shrink. So let's see what it looks like on the graph. Now the parabola has shrunk. It has the exact same roots it had. Notice the y-intercept changed from negative 8 to negative 4. So did the symmetrical point with that. This, by the way, the axis of symmetry is at 1.5, which makes it a little tougher to graph, but everything else is the same. All right, so let's review. Find a quadratic function from the roots. Pause the video and do it yourself. Multiply that function by 3. In other words, do 3 times f of x. (36 times 3) and since we multiplied by a whole number, that's called a vertical stretch. There is a horizontal stretch. We're not doing that this year. We're only stretching them and shrinking them vertically up and down. Take the original function, multiply by 1/2, and that's a vertical shrink. Okay, some of you may have noticed a pattern. We're changing the subject now. May have noticed a pattern in the more complicated quadratic functions yesterday. So what if we have the roots at fractions, 1/2 and 3/4? What made that answer? Well, it turns out that you take the denominator and put it in front of x. You subtract the numerator, and you get the factor that made that root. It's the denominator in front of x minus the numerator. D stands for denominator, N stands for numerator. Then you would write the function, 2x times 4x, 8x squared, 2x outer, 2x minus 3, negative 6x, inner, negative 4x, negative 10x, last, plus 3. So try this one on your own. Pause the video. With a negative 1/3, right, where it's going to be plus. So it's going to be 3x plus 1. So we have 8x minus 15x minus 7x minus 5. So notice I wrote whole number terms here, because some people get the great idea, why can't I write x minus 2/3? But we never had factors that look like that, so you're not allowed to do that. So the factors that made 2/3 were 3x minus 2. The factor that made negative 5 was x plus 5. And you do f of x, and you FOIL it, 3x squared plus 15x minus 2x plus 13x minus 10. You can multiply that by 5. You can multiply that 1/3. I'm going to let you do the rest of this lesson because I'm running out of time. YouTube won't let me put more than a 15-minute video up, so I've had to sort of rush up. But there's final question. You can do that. And the last thing I'll leave you with is our Easter egg of the day. I have never told any students my birthday, and I'm still not. But what I will tell you is, may the force be with you.